Alright, my name is Alexander Gardere, and this is the effect of cold temperature on 3D printed concrete. Now, 3D printing is an additive manufacturing process that prints layers in an XYZ coordinate system. Layer upon layer is laid down through an extruding nozzle, and a desired shape is created. In this case, for construction, it would be either individual pieces that can be assembled later, or an entire building. 3D printing has been around as a technology, been around since the 1980s. It's found plenty of use within manufacturing, specifically for prototyping. And more recently, it's been finding uses in other industries such as medical, or in this case, construction. Contour Crafting Inc. Is the first American company to adapt it to a construction scale. According to their estimates, 3D printing can reduce costs up to 80% of conventional building. This is through shorter project lengths, more efficient uses of materials. Due to being an additive manufacturing process, there's less excess, and there will be virtually or almost no labor costs whatsoever. This will also increase safety within the industry as a whole. The construction industry has an exceptionally high accident rate, so this would make litigation costs for any sort of thing like that just much more affordable. But like I said, as it is automation, it will replace jobs if it's ever adapted in a mainstream level. And this is due to everything being taken care of by a machine. Currently, there's plenty of limitations that are keeping it from being a mainstream technology, and this is mostly because it's still in its infancy. There's only a few companies that are actually capable or have developed a construction scale printer, and because it's intellectual property and there's patents involved, they are not very keen on sharing their research. So there's not really a lot of accessible research currently available. Then there's the logistical problems. Materials conventionally, for conventional projects, you only have to have your materials as needed, and this can be over the course of weeks, months, whatever. But for 3D printing, if you're printing something in, a day or two, you need all of your materials all at once. So this creates a lot of stress on supply chains, and then there's the issue of actually moving the printer around. So even on smaller projects, these printers are going to weigh a couple tons. That's not easy to move around, especially if it's like a giant crane system or an arm system like the Aspis Core printer. Then there's material limitations. Metals have currently gotten Metal 3D printing has gotten much better recently, but it's still expensive and still extremely slow. So scaling it up to a 3D level is non-feasible. Then there's plastics and resins. This is also really expensive. It's not as durable as metal or concrete, usually. But it's still extremely expensive, especially resins. Then there's concrete and cementitious mixtures. Strong and durable, just as always, but it's extremely difficult to print with due to a few specific traits. So, 3D printed concrete has a plastic-like consistency versus conventional concrete, which is meant to fill in forms or be laid into a slab. This will pretty much stay however it's extruded. It uses small aggregate sizes, a nominal size less than 3 millimeters, and then it's going to utilize admixtures to improve the extrudability of the mix, and mixtures that will promote mixture cohesion to further improve the initial stability of the concrete. So, 3D printed concrete, one of the main issues currently that affect it is this printability window. This is its initial stability, as I mentioned before, and its printability limit. Now, the initial stability is each layer's ability to retain its shape without deformation from its own weight or from subsequent layers. The initial yield stress usually increases over time in a linear fashion up to its set point. And the same reason that it starts to gain strength is the same reason there's a printability limit. This is the point at which concrete can no longer be extruded from the printing nozzle to form acceptable layers. If you leave the concrete into the printer too long, it'll set and probably ruin your printer, or at least the nozzle, because you have to get everything out. Now, printable concrete, So, cold temperatures affect this printability window substantially. Conventional concrete practices avoid cold due to decreasing the amount of workability and also slowing the initial set of the concrete. This is usually pretty bad. You kind of need concrete to actually fill into forms to create shapes. But when we're talking about 3D printed concrete, this is actually somewhat advantageous as it increases the initial yield stress of the concrete, and workability can be altered with admixtures. And because it has a longer set point, the print window is extended as the set time goes from around 4 to 5 hours to around 20 at very low temperatures. So, the research objective for this is to create a printable concrete mix that functions at low temperatures and to gain better understanding of this print window in cold environments. Quantitative analysis of cold printed concrete is needed to establish if this is a valid option to extend the print window in colder climates. For this experiment, our concrete mixture design, we'll have to further tweak it to get it just right, but it's going to use a type 2 Portland cement, nominal aggregate size of less than 3 millimeters. It'll utilize a high-range water reducer and viscosity modifying admixture to get the right consistency so it can be extruded. Our cement and water ratio will have to be identical for each of our mixtures, which we're going to have 4 of total. And our 4 concretes we will be testing will be, as a control, 1 without any of these admixtures, 1 with silica fume, 1 with nanoclay, and 1 with polypropylene fibers. Each of these help increase cohesion for the mixture and increase strength, compressive strength for the concrete. How we'll test this will be through the stability test. The stability test will be used to measure everything. This is before and after pictures, essentially. We'll be using a ruler as a benchmark. What you do is you print out an initial layer, and the second layer will be placed based on one of our time gaps, which will be at 0 minutes, so immediately after 15 minutes, and then 30 minutes. And this will help establish our initial stability for each layer. And we'll be doing this at 30 degrees, 50 degrees, and 70 degrees, or 70 degree temperature will be our control group. And we'll repeat this experiment 3 times total. So we'll take a picture of these. We'll have a ruler just in front, like there. And we'll take a picture and analyze that with image processing software such as ImageJ. From there, we can average all of our results and display them in a data chart based on our 3 variables: temperature, time, and concrete admixture. So, testing printability. Sorry I jumped around there a little bit. Next we'll be testing the printability limit. This is pretty easy to test. You really just have to run the printer until it can no longer print acceptable layers. It'll end up forming inconsistent layers such as this one right here. So it'll have kind of jagged edges. It won't be uniform in any sense. And we can just record when it hits this limit at each temperature for each admixture. And we'll record this 3 times for more consistency, and we'll show this in a data chart. So from here, we'll have both our initial set and our print limit. So we will then be able to show our total printability window, which will be the total time at each temperature for each cement mixture. This will show the total average data for each concrete mixture at the established time intervals and for each temperature. And we can see the total print window and conclude whether or not cold weather has indeed lengthened the print window. So, preliminary results. Cold printed concrete can expand the period in which a batch of concrete can be printed, especially in cold temperatures. This is due to cold weather increasing the initial yield stress of concrete to promote more labor stability and lengthen the amount of time required for the concrete to set. As a whole, the study, there's not really a lot of information regarding extreme environments with 3D printing that's readily available to academics. So hopefully this study will fill in some of this research gap. With more research, construction scale 3D printing has the potential to make the industry more time and cost efficient, and hopefully make things better for the rest of us. Thanks. That is all.